A common ion occurs when you have an acid or a base solution and a salt containing that same ion. So when you mix hydrofluoric acid and sodium fluoride, the common ion, what do you think that's going to be? Fluorine, since both of them are producing the fluorine ion. Common ion effect is the shift in equilibrium position that occurs because of the addition of an ion already involved in the equilibrium reaction. If you have HF, it dissociates into hydrogen and fluorine ions. If we already have some fluorine, then it's going to shift it back to the left due to Le Chatelier's principle. So we're going to have less hydrogen ions as well. If we have less hydrogen ions, it's going to be less acidic because of the reaction shifting left. So if you already start with products, then we aren't going to need as many products for it to reach equilibrium. So in this problem, we have a hydrofluoric acid solution that has a Ka of 7.2 times 10 to the negative fourth, and they want to calculate the concentration of H if we have HF and sodium fluoride. So you write the dissociation of the acid and then write your molarity of each substance in there. I have 1 molarity HF, and because I have sodium fluoride, I also have 1 molarity of fluorine ion. That came from the sodium fluoride. Then you do a regular ice table. But just notice we have to include the 1 plus X for fluorine since we already had some due to the soluble salt breaking up. So write our dissociation equation, plug everything in. We can ignore the minus and plus x's since Ka is very small. And so our X or H concentration is equal to 7.2 times 10 to the negative fourth. We can calculate the percent dissociation. Remember, the equation for that is our concentration of H over original concentration. So we put our H over our original concentration of 1 times 100 gives us our percent dissociation. Of 0.072. Notice this is much less than if we had HF by itself, in which case it would have been 2.7%. So a buffer is a solution that resists change in pH whether you add acid or base to that. The best example of a buffer is your blood. It's able to withstand small amounts of acid or base without changing pH. So there's 5 ways that you can have a buffer. The most important is you have to have a weak acid and weak base. So 4 ways that you can get that is if you have a weak acid and its salt, because its salt would be basic, weak base and its salt, weak base and half the moles of a strong acid, or weak acid and half the moles of the strong base. So here it says we have a buffered solution, we have acetic acid and sodium acetate. They both have acetate in them, so we have a weak acid and its conjugate base. So always start with the actual acid or base, so in this case acetic acid, and write the dissociation equation. We have 0.5 acetic acid, and we have 0.5 sodium acetate. The key with the buffer is you always have a reactant and a product. Okay, your salt's always going to dissociate 100%, giving us a 0.5 molarity. Set up your ice table, and then solve for X. So our X, or concentration of H, is 1.8 times 10 to the negative fifth. So our pH is 4.74. When you add an acid or base to a buffer, first you need to figure out which part of the buffer is going to react with the substance that's being added. Then you're going to solve with stoichiometry until one of the reactants is used completely up. You have to have moles. And finally, set up an ice table. So here we want to know the change that occurs when we add solid sodium hydroxide to a buffered solution that was in the previous problem. In the previous problem we had acetic acid, and it was at a 0.5 molarity, and we had sodium acetate also at a 0.5 molarity. It says we have 1 liter of that buffered solution. We're adding NaOH, which is a strong base, so it's got to react with an acid. So we figure out which part of our buffer is the acid, in this case it's acetic acid, and we write our equation out. You can leave the sodiums or you can remove them since they're just spectators. You can ignore the water, and you need moles of each substance. They gave us the moles of NaOH. We had 0.5 molarity, 1 liter, so that's 0.5 moles of acetic acid, and 0.5 moles of sodium acetate. We're going to react them. So the smaller amount's going to be used up completely. Make sure that you add the 0.01 to the products. Basically, our smaller number is our X that we would normally be solving for. You've got to convert it back to liter, or back to molarity. Even though it's 1 liter, going to get in the habit of plugging it in. So it's 0.49 molarity and 0.51. Look and see what you have. We have acetic acid and sodium acetate. Together, those make a buffer. So the last step was use an ice table. So we're going to start with the actual acid, which was acetic acid. Dissociate it. And plug in those values that we just had. plug it into our Ka expression. And solve for X, which is our hydrogen ion concentration, which is 1.73 times 10 to the negative fifth. So our pH is 4.76. So notice our pH did not change very much. It was 4.74 and it went up to 4.76. So we had an increase of 0.02. It wants us to compare this change with that occurs when we add that amount of sodium hydroxide to water. So our concentration of sodium hydroxide is our concentration of OH. Our starting pH is 7 because water is neutral. When NaOH dissociates, it breaks up into sodium and hydroxide. So again, if we have 0.01 moles in 1 liter, that's 0.01 molarity, 0.01 molarity, and 0.01 molarity. So our concentration of OH is 0.01. So POH is 2, pH is 12. So in this case, our pH change was a positive 5. Which was much larger than when we added it to our buffer. On this one, we have 40 milliliters of HCl and 200 milliliters of HCN. First, you need to figure out what you actually are starting with. HCl is a strong acid, and HCN is a weak acid. Remember, when you have a mixture of two acids, only the stronger acid is going to affect the pH. So we can really ignore the HCN except for the fact that we have 40 milliliters and 200 milliliters. So our final volume is going to be different than what we started with. So the concentration of HCl at the end is not 0.02. So first you need to figure out your your original moles of HCl. Then find your new molarity by finding the new volume. So first we find our moles of HCl, which is 8 times 10 to the negative fourth. We divide this by total volume, which was 240 milliliters. Which gives you 0.0033 molarity of hydrogen. So pH is 0.247. In a buffered solution, the pH is governed by the ratio of acid to base. So you have the equation below, which is basically just a rearranged Ka equation. The larger our acid and base are compared to the OH, the smaller the pH change will be. So there's our Ka expression. Notice they just rearranged it. Okay, and the larger the acid and base concentrations in the buffer are, the more effective it's going to be. The more acid or base you can add to it and the pH not change. So the Henderson-Hasselbalch equation is useful for buffers when you know the acid and base concentrations. It's pH equals pKa plus log of base over acid. Okay, you can use the top equation or the bottom. They both mean the same thing. If we look back at that equation, all they did was log everything. The log of H is pH. The log of Ka is pKa. And they logged acid over base, but when they did that, that turned it into negative log. So that's why they flipped it in the equation and why it's base over acid, to make that a positive value. Alright, so here we have a pH of a solution containing lactic acid and sodium lactate. Okay, that's our acid. Sodium lactate is its conjugate, which is a base. We could solve this using an ice table, like we did previously, or because it's a buffer and we know our concentrations, we can use Henderson-Hasselbalch, which will be a lot quicker. So we know we're looking for our pH. If we take the negative log of our Ka, we get 3.85 plus log of base. Well, lactic acid is our acid, so sodium lactate must be our base, so 0.25 over 0.75. So our pH is 3.37. Alright, on this one we have NH3 and ammonium chloride. It's the exact same thing except we have a base. Remember that the equation is pKa, not pKb, so you have to find your Ka before you can plug it into your equation. So we have ammonia, which is a base, and ammonium chloride, which is its conjugate acid. So we figure out our Ka, and it's 5.56 times 10 to the negative 10th. And you get that from Kw is equal to Ka times Kb. So 1 times 10 to the negative 14th over our Kb gives us our Ka. Our pKa was 9.25. We know our concentrations because they gave it to us. And so our pH is 9.05. Okay, go ahead and try this one on your own, and then you can restart it. Alright, so first thing you need to do is figure out what you have. We have CH3NH2, which is an acid, because they gave us a Ka for it, and then we have NaOH, which is a strong base. So the first thing they're going to do is react, because we have an acid and a strong base. So if you have something strong and its opposite, they're going to react. Okay, our acid should lose a hydrogen, so we get that. And I'm going to leave off the sodiums just for simplicity's sake. You could have left it, you would have had to put it on the CH3NH, though. Remember, when it's reacting, you have to have moles. So we have 0.2 times 0.06 and 0.2 times 0.06 for our acid, which gives us 0.012 moles and 0.012 moles. And we don't have any CH3NH. We subtract the smallest, which in this case is the same. And we're left with 0.012 moles of the CH3NH. Remember, we can't use moles, we need molarity, so we divide by total volume, which is 0.102 liters, giving us a molarity of 0.1. Remember, finally, you're going to do the ice table because we don't have a buffer. Because all we are left with is one thing. In order for it to be a buffer, we would have had to have CH3NH2 and CH3NH left over. So since we only have a weak base, we're going to do our ice table, and if it's a base, we need to add water to it so it has something to gain a hydrogen from, just like we did in the previous chapter. We do our ice table. When we solve for X, we're going to get our OH concentration. Be careful, they gave you the Ka for CH3NH2, which means you need the Kb because we didn't start with an acid. We started with its conjugate base. We have our Kb, and now we plug it into our Kb expression, solving for X, which is our OH concentration. You get 4.8 times 10 to the negative 6. So POH is 5.32. pH is 8.68. Go ahead and try this one on your own and then restart. Alright, so we are mixing HCN, which is a weak acid, and sodium cyanide, which is its conjugate base. Together, they're a buffer. If it's a buffer, we know our concentrations, so we can use our Henderson-Hasselbalch equation. We get our pH. It's equal to 9.62. But if you look at the problem, it wanted to know the POH. So we can subtract that from 14 to get our POH of 4.38.